Hi Pre-Calculus, here we are. We are looking at section 5.4 and we are working on applying trigonometric functions. Our vocabulary phrases are only two. One is angle of elevation, and that's when we are in a low place and we're looking up. We would make the angle of elevation the horizontal line or the horizon in a sense, and we think about what angle we are looking up, what's that opening that happens there. So that's the angle of elevation. And then the angle of depression would be if you are looking down, we would consider the horizontal line, and then the opening downward as the angle of depression. And if you notice, I colored these wrong, so my bad. My highlighting was off. Let's look at the first example. The first example we have here is example 1, where we're given some information about this right triangle. And let's just kind of orient ourselves a bit. The right triangle has a hypotenuse of 14. It has an angle of 35 degrees. We can find this angle by, just using the fact that the angle addition, the sum of the interior angles of a triangle is 180. We'll see if we need that. Let's not do more work than we need. And we are asked, given that if we have angle P is 35 degrees and side R, which is the hypotenuse, is 14, find side Q. And so I've highlighted here these two sides, and what do these two sides relate to in reference to our trigonometric relationship? So we know we've got SOHCAHTOA, which gives us the relationship of sine, cosine, and tangent, and from that we can infer the other trig identities or trig relations. I'm looking at ka or cosine because the cosine of 35 degrees is going to give me the adjacent over hypotenuse. So when we're doing problems like this, you want to use what you've got to get what you want. And what I have is the hypotenuse. So I knew I wasn't going to use tangent. And I'm looking for the adjacent to 35 degrees or to P, and therefore I needed to use this one. So now we're going to pull out our calculator and we're going to use that to answer this question. So watch, we'll find the cosine of 35 degrees. If you're using a calculator, make sure you're in degrees and not radians, something we'll talk about later. The hypotenuse is 14 and we are looking for the adjacent side. So we can do a couple things. Since I'm looking for this adjacent side, I'm going to solve for a already. And so 14 times the cosine of 35 is going to be equal to my answer. I like doing this because I call it making it calculator ready. So I'm just going to plug all this information into the calculator, 14 times cosine of 35, and then I'm going to get my answer, and that'll be it. I'll be done. And I did just that, and here I have that the length of side Q, which I have as A because it's an adjacent side, but I should have put Q. The length of side Q is 11.468 units, whatever the unit of length is there. So this example 2 refers to information given in the beginning of the chapter, but let's go ahead and just take a look. I think we can do it without backstory. So refer to the application here. If the angle that the rope makes with the level ground is 52 degrees and 15 minutes, how long is the rope? So let's go ahead and check out the information. We know that this is the height. So if we're standing at this angle, we're given the opposite, and we want to find the hypotenuse, which is the length of the rope. So if we go back to our SOHCAHTOA business, we know that we should probably use the sine, right? Because opposite over hypotenuse is the sine. So the sine of 52 degrees and 15 minutes, yes, I'm going to change the 15 minutes, but the sine of 52 degrees and 15 minutes should be equal to 40 over R. Now here's the thing, I want to solve for R. First I'm going to get rid of this 52 degrees and 15 minutes. You guys remember how to do it? 52 degrees is going to stay the same, but I'm going to add to that 15 over 60. Does that make sense? Because we know that 60 minutes gives me 1 degree. So this is 15/60th of a degree, right? And so we know that 15 over 60 is 1/4. I'm hoping I know that. Yeah. So that's 1/4, and we know 1/4 is really 0.25. So we know that this is 52.25 degrees. Look at that palindrome. Super cute, 5225. Okay, so we're going to put that here instead. So sine of 52.25 degrees, and then we want to solve for R. And to solve for R, there's a lot of ways to do it. Multiply r over here, then do this. Basically, what I do whenever I have something that I want to solve for that's in the denominator, I'm going to take the reciprocal of both sides. So now this is going to be 1 over the sine of this angle, and that's going to be equal to r over 40. Totally legit. And the final thing I'm going to do is multiply both sides by 40. So I've got 40 over, you see what I'm saying? The sine of this angle, 52.25, and that's going to equal r. Before I start anything, I like to make a calculator ready because I honestly don't want to take the sine of that angle and have all of these decimals to then come back and divide 40 by. So I want to just go ahead and plug it into my calculator. I'm going to put 40 and I'm going to divide by the sine of 52.25. So I'm getting that r, that rope length, is equal to 50.589 feet. And so I got feet from this picture, and so that's cool. So what is the distance between the bottom of the tent and the stake? So now they want us to know or determine d. So what I'm going to do is I'm going to shrink all this business out of the way, put it over here. So if you want to reference it, no, nobody can see it there. But anyway, let's go ahead and do part B. Part B, yeah. So we're looking for D. So again, we need to stand here. We know this angle to be 52.25. So what are we finding the sine, cosine, or tangent of it? I've got the adjacent, and I like to use what I've got to get what I want. Why I'm saying that is I could use R, but R to me is a little bit not as exact because it was not a given bit of information. And if I'm taking an assessment, if I don't have to use information I calculated, I won't, because if I made a mistake, I'm not going to carry that mistake into another problem. Just my idea. Okay, so now as I'm looking at this, I'm doing opposite over adjacent. I know that's tangent, so the tangent of 52.25 is equal to 40 over d, and so we can do pretty much the same thing where I take the reciprocal of both sides, and what I'm going to end up with is that d is equal to 40 over the tangent of 52.25, and I'll do the same thing. I'm going to calculate that 52.25 like that. I'm going to calculate that and be back with my answer. So with that, I get that D is equal to 30.971. Again, R is equal to 50.589. And sometimes you need to really look at your problem and say, does this make sense? And it does make sense that this should be the longest side as it is the hypotenuse. And it makes sense that this should be around this neighborhood. In fact, if you think about it, you might remember a 3, 4, 5 right triangle. So 3 squared plus 4 squared equals 5 squared, which proves that it's the size of a right triangle given Pythagorean theorem. You can see this kind of has that vibe. 40, and this isn't exactly 50, and this isn't exactly 30. So, you want to make sure and check that your answers make sense. Example 3, a regular pentagon is inscribed in a circle with a diameter of 8.34 centimeters. The apothem, that's this line here, of a regular polygon is the measure of a line segment from the center of the polygon to the midpoint of one of its sides. Find the apothem. So we want to find that length. And I feel like for this, I'm going to zoom in a little bit closer. So let me see how I can do that without being ridiculous. Okay, so here we have the situation. We need to find this length here, and I'll highlight that just to keep our focus and attention on what we're looking for, the apothem. And so what we'll do first is see if we can find whatever information we have about this particular figure. First, we're dealing with an isosceles triangle here, this larger triangle. So I know that this is a 4.17 because the center to the each vertex is going to be the same length because it is the radius of the circle, right? Okay, so now that we can confirm that, we can get some information about, let's say, the angles here. So how many of these types of triangles would we have? We'd have 1, 2, 3, 4, 5. And so if I'm looking at, again, this angle here, if I can find this angle, then I can find this alpha, and that'll start giving me some information. So watch this. I know that all around this is 360, right? So this one angle that I'm calling x, which we'll cut in half to get alpha, is 1/5 of 360. So 360 divided by 5 is going to give me that answer. And so you know, and I know that we're going to get, I don't know what I'm going to get. We're going to get 72. Yeah? Yeah. Okay. So if I have 72 here, I know that alpha is going to be 36 degrees. Make sense? All right, so now that I know that that's 36, maybe I can get some more information, or do I need more? They asked me to find the, let's see, find the apothem, right? That's why I highlighted it so I can remember. Okay, so we're finding the apothem. I guess we don't need any more information, do we? We have enough to do the thing. So I'm going to scooch in a little bit more. If this is 36 degrees, right here, if this is 36, then I'm looking at a right triangle where we've got 36 degrees. The hypotenuse is 4.17, and the side we're looking for, according to the angle that we're standing at, is adjacent. So that's going to be the cosine of 36 degrees is going to be equal to the apothem over 4.17, and I'm going to just take that 4.17, multiply it by the cosine of 36, plug all that into my calculator, and I will find out the apothem is equal to approximately 3.374. All right, not too bad. Let's try another. Example 4. On May 18th, 1980, Mount St. Helens, a volcano in Washington, erupted with such force that the top of the mountain was blown off. To determine the new height of the summit of Mount St. Helens, a surveyor measured the angle of elevation to the top of the volcano to be 37 degrees and 46 minutes. The surveyor then moved 1,000 feet closer to the volcano and measured the angle of elevation to be 40 degrees and 30 minutes, determined the new height of Mount St. Helens. So what I started off with is just changing this to degrees, so it's going to be more convenient for us to use in our calculator. So this became 76 degrees. Again, I took 46 divided it by 60, got 0.7666 repeating, my bad, not 76 degrees, but 37.76 repeating degrees. And then this is just 30 over 60, which is 0.5, and so we have 40.5 degrees. All right, done. Now we've got to figure out how to set up this situation. We are asked to find h, so let's hold on to that as the goal. We're given some information, and I don't know about you, but sometimes it's really uncomfortable to have two variables. So how can I use this as a guide? So there was one measurement taken here, and then moving back 1,000 feet taken here. How can we figure out h? Do we have to figure out x in order to figure out h? All very good questions. Let's set up some trigonometric relationships. So usually tangent is the trig relationship that we're going to talk about when we're dealing with angle of elevation and angle, because that's what this is, and angle of depression, because you're not usually given the length of the view or of that angle, but what you are usually given is the height and the vertical and the horizontal movement there. So the tangent of 37.76 degrees, right, is going to be h over 1,000 plus x. And then again, the tangent of 40.5 degrees is going to be h over x. So with a little bit of algebraic manipulation, I can get that x is equal to this h over the tangent of 40.5 degrees, and then I can take this same x and substitute it in there. And the benefit is that I have one equation with one known as opposed to two equations with one unknown, right? Or with two unknowns. Okay, so it happened. I did my substitution, and I don't know, I probably want to do some more. Maybe I'll multiply both sides to get this h out of the denominator by this whole denominator and see what happens. Okay, this happened. So I think I'm going to keep going. You know what I'm trying to do, guys. I am trying to get h by itself so I can make my problem calculator ready. So I'll just plug in a bunch of stuff in the calculator and I'll be done. I don't want to carry around decimals. Let's see how well I fare. So the next thing I'm going to do is I am going to do the distributive property. I'm going to try to get h by itself, move it over to the other side, and do some things. Are you guys along for the ride with me? I'm glad. Let's keep going. Okay, I'll be honest, I'm a little tired of what I did, but I did do the thing. So let's go ahead and recap. So we started off with, gosh, where did we start? We did our substitution. We moved over here. We had the tangent of 37.76. This should be 76 repeating, but we'll just leave it at that. We distributed that through. Once we did that, we ended up with this. I need to get all the h's on one side, so I moved this bad boy over here. You see that? So I'm left with just 1,000 times the tangent of 37.76, repeating, and this is repeating too. And then that happened. All right, now I need to factor out the h. I know what you're thinking. It was not worth it, and I'm kind of in agreement too, but I'm going to go with it because I started. So I factor out the h. I now have the h almost by itself, and then I'm going to divide both sides by this thing, the tangent, 1 minus the tangent of 37.76 over tangent of 40.5. I know it took a long time, but I just wanted to have a calculator ready or Desmos ready so I can just put all the information in there and not have to like carry around decimals. You might be saying, what can we have done instead of this? We hate this. What you could have done is calculated what the tangent of 37.76 is and 40.5 and had maybe an easier time of moving things around instead of moving around all of this trigonometric jibber jabber. So now I'm going to plug it into the calculator. I'll pause. Okay, I did this twice. I'm not sure which one you can see. My screen has an interesting capture situation. But anyway, so I plugged all this in and I'm looking at it and I get this. Here's what I want you to remember if you're using Desmos. Make sure you come over to the side and change it from radians to degrees. And now we get an answer that looks more like it's situated for our situation. So I don't know if you would like to do it this way, the way I did it, or if you'd rather just put the values in there beforehand. But we get that the height of Mount St. Helens is 8,340, let's say 0.8 feet now. I think they're doing it and wanted it to, but that's okay. All right, I look forward to talking to you guys soon. Let me know if there's any questions or concerns. Take it easy. Bye-bye.